This section I would like to title the Normal Distribution Part 3. And what we're now going to do, we're going to actually use area under the curve to find specific values for x. Suppose we were interested in, say, we had a problem with, we know the mean and standard deviation, and we know the percentile. Could we find the value then that corresponds to that percentile? And yes, we can, using the techniques in this section. So the first thing we're going to look at is the process of knowing the area and finding the z-score, which, as I mentioned in the blue paragraph, I refer to this as a reverse chart lookup. In other words, we're going to go inside the chart, find the area, and then see what z that corresponds to. Now, these first two examples I'm going to cover fit exactly on the normal curve, but not every problem will fit like that. We'll see how that comes about, and we'll generally choose the closest one to it. So the first one says we're going to find a z-score that has 59.1% of its distribution to the left. Now, the calculator can do this too. I'll show you the chart and I'll show you the calculator. First thing I'll do is bring up the chart, 59.10% to the left. Remember, our normal chart is based on area to the left. So I'm going to scroll down here. I'm looking inside the chart. So anything above 50% is going to be on the positive side. And right here we have it. 59.5910 translates back. It's on a row of 0.2, column of 0.03. Therefore, the z-score would be 0.23, which is what we have here. Now, the next one says find the z-score that has 96.16% of the area to the right. All right, now it's a little bit different, area to the right. Now, we can't look for 0.9616 on the right because the chart's based on the area to the left. So I have to take 1 minus that amount to figure out what my area to the left is. So over here to the right, I have 1 minus 0.96 equals 0.0384. So that's the value we're going to look up on the chart, 0.0384, which will be on the negative side. And it is right, scroll over here. And I'll zoom out, and that's in the negative 1.7 row. Scroll up to the top, that is the 0.07 column. So my z-score would be negative 1.77, which I have here. Now, the inverse norm function in the calculator, bring that up and show you real quick where that is. If you go second distribution, as I mentioned there in the notes, it's right there below the normal CDF. So, and what the argument for the inverse norm is, it is area to the z that represents area to the left. It only knows left. So if I put in 0.190, I get, and we round that to 2 decimal places for our z. You know, probabilities we use 4. For the z we only need 2, so that's 0.23. Now, when we go back to the notes here, you'll see that now for the one area to the right, actually, you know, you can do 1 minus the area first, or you can just put 1 minus directly in the calculator. 9616, and you don't have to even put the number in there, the 0384, and there's our negative 1.77. So the inverse norm only has one argument to it, unlike the normal CDF, which has 2 things, the low and high. Area to the left, that's it. So if it's not area to the left, we make it to the left. Now, most of the time, this is not going to be an issue because we're going to pretty much be dealing primarily with area to the left anyway. All right. So, and that leads us to finding a z-score given a percentile. Now, we talked earlier on in the course about percentiles. Specifically, we did quartiles calculations. I didn't do any percentile calculations until now. But anyway, the idea behind a percentile, that means that's how much of your distribution you have of values that are to the left of that percentile. For example, the 82nd percentile means 82% of your scores are to the left of that number. So we'll do this for what I call reverse chart lookup, which is not an official name or whatever, but that's a process we'll use to find this but you'll be able to use the inverse norm in the calculator. See the notation right here is written as P with a subscript. So P35 would be 35th percentile. So now we're saying find the z-score that corresponds to each percentile. Here's a P20 for 20th percentile, P99 for 99th percentile. Now I have a little sketch here. That's not necessary, but the 0.2 area to the left, that certainly guarantees that our z is going to be negative. In fact, if your percentile is less than 50, your z is negative. If it's greater than 50, it's positive. If it was 50, that would just be your median, which is the same as the mean in the normal distribution. So it would be 0. So it's going to be over here to the left. Now I'm going to go to the chart here. I'm looking for closest 0.2. Now this will be the first time that we don't have one that fits exactly. Scroll down here. I look, and what I like to do is identify the two numbers that immediately the one below and the one above my number that I'm interested in. So I found a 2005 and a 1977. So our goal here is to pick the closest one. Above or below is irrelevant. You just want the one that's the closest. And 2005 would be closest to 0.2. And you could subtract both numbers from 0.2, and you could take the absolute value, and whichever one's the smallest, that means that would be the closest number. So I'm going to pick 0.2005, which is in the negative 0.8 row, and scroll up here, it's in the 0.04 column. So my z would be negative 0.84. And then here I have a handwritten where I show this 2005 and the 1977. And closest to 0.2, and there it is. Negative 0.84 is the z value that corresponds with the 20th percentile. Now the next one, the 99th percentile. So I'll go back to the cumulative normal chart. Closest to 0.99. And let's see what we have here. 9. Here we go. 0.99 would fit right between those two numbers, 9898 and 9901. But 0.9901 is actually a little bit closer than 9898. It's in the 2.3 row, the 0.03 column, so it would give us a z-score of 2.33. And I have a little cutout snippet from the chart right here, what we just looked at. 0.9898, 90901, there it is. So the P99, which is a z-score, would have a z value of 2.33. Notice right here I have the calculator cut out for the inverse norm for both of these. And percentiles, you will never have to do 1 minus. It's always going to be just inverse norm of the percentile. So it's because percentile is always area to the left. Inverse norm of 0.2, then there's your negative 0.84. Inverse norm of 0.99 is 2.33. Now, so let's see how we're going to use this information to come up with the x values. Like I was mentioning earlier about, knowing the mean and the standard deviation and the percentile, can we calculate the score or value that goes with that percentile? And that's what we mean by x value here. We want the score that goes with a certain percentile. Now here's the formula that transforms a z-score to a data value x in a given population. It's x equals mu plus z sigma. And all this formula really is just your standard z-score formula. And if you just did a little algebra to it and solved for the variable x, you would come up with this expression. So it's not really a new formula. It's just the same z-score formula rearranged and isolated for variable x. Now here's an example I'll leave for you to look at. Now here's where the z-scores are already given to you. In other words, most of the time we're going to be working with percentiles. But here it's just showing how to use the formula essentially. We have a mean of 67, standard deviation of 4, and based on 3 scores of 1.96, negative 2.33, and 0, we'd plug those in for our respective z's and then come up with these values, 74.84 57.68, and 67. But what we're most likely going to be doing here is taking a percentile, coming up with that z-score, and then using this formula as they did here. So we'll have one extra step in our problem. All right. So let's look at this example. In a survey of men in the U.S. ages 20 to 29, the mean height was 69.6 inches with a standard deviation of 3.0 inches. Assume the data is normally distributed. What height represents the 80th percentile? So we're trying to find the height. Men in that age group who would be taller than 80% of men in that age group. So we will use this transformation formula first, but the first thing we have to do, so here's the formula, is we have to find the z-score that corresponds to a percentile of 0.80. Okay. So from the chart, which I already have clipped out, so I'll go ahead and just use this. Let me zoom in on this for a second. You can see right over here, so my 0.8 would be pinpointed between 7995 and 8023. It's closer to 7995, so that's the one we would pick. So it's on the 0.8 row, 0.04 column, so my P percentile value is 0.84. So I'm going to write P of 80 is 0.84. Now I'll do the inverse norm in the calculator real quick. Inverse norm 0.8. And there we have point. Okay, let's copy that. So either way, use the chart, we can use the calculator, whatever is convenient for you. And now we're ready to plug in our formula. Keep in mind our problem is going to give us the mean and standard deviation every time. So all we have to do is use our formula right up here. X equals mu plus sigma z. In fact, I guess I can copy this down just off to the side here so we can see it. So X will equal, from back up there, 69.6, the mean, plus Z that we just found is 0.84, and the standard deviation, which is 3. And that's going to give us, move this over, calculate this, 69.6 plus 3 times 0.84, 72.12. So 72.12 inches would represent, as a statement I have below, that 80% of the males have a height of less than 72.12 inches. Now I'm going to show you another little calculator trick which you can do here. In fact, I'll just get rid of this box for a second, since we've already seen this. You know, if you're doing this in the calculator, you can actually do this problem all in one step. In other words, you can go 69.6 plus second distribution inverse norm 0.8 times the standard deviation of 3. And there we have it. So you see, you really don't have to get that percentile number separately if you don't want to. You can just calculate it that way. Go straight to the answer. Now, part B for this problem says, what height represents the first quartile? Okay, going back to what we learned earlier about quartiles, the first quartile is the same thing as the 25th percentile. You know, hence the fact it's breaking the data into quarters. So the z value for P25, we want to find the closest one. So there's the two I pinpointed, 2514 and 2483. It's a little closer to 0.25. If it's exactly in the middle, which we'll see this come up in the next chapter, or chapter 8, we can use a 0.5 as a third decimal place. But for right now, I don't think you'll have any on test where it's exactly in the middle, but if it was, you could really pick either one of them. We won't worry about a third decimal place at this point in time. But that one's actually pretty close, but it's closer to negative 0.67. So P of 25 is definitely negative 0.67. All right. Now, so I can write this out as x equals $69.6 plus my z of negative 0.67 times standard deviation of 3. So I'll use the answer that I already have written below, but I'll put this in there. 67.9 inches. So in that age range, if you're a male at 67.59 inches tall, you're higher than 25%. You're taller than 25% of the males in that age group. And the calculator, I can use that same little trick I use right here. I'll do second enter. All I got to do is come over here and just change the inverse norm to 0.25. And there it is. 67.57. So you can use that same technique again, and you don't have to really identify the z-score at all. Now here's an example that where they put the third decimal place in there, and we will see this in Chapter 8. Scores for a civil service exam are normally distributed with a mean of 75, standard deviation of 6.5. To be eligible for civil service, you must score in the top 5%. So that basically means top 5%, as drawn on the graph here, is representing the 95th percentile. I mean, in other words, you've got to be at the 95th percentile minimum. So anything higher than that takes you to, you're good at 95% or higher. But all we have to do is we're trying to find that cutoff score that represents the 95th percentile. So as you can see from this picture, we have 95% of the area to the left. And this is one of those ones where it fits right between the two. And they'll use actually 1.645 because it's right between. It's like the average of 1.64 and 1.65. Add them together, divide by 2, it's 1.645. So using the same equation, which they've done here, you take the mean 75 plus that z of 1.645 times the standard deviation of 6.5, and we'll get a score of 85.69. Which may not be a score you can actually make, so in reality this might have to be rounded to a number, see which they've done here. So you see they've just turned this into rounded up to an 86 as the actual score. All right, here we'll work out this next example. Suppose Geddy Lee was told that his score on an accounting exam was the 90th percentile. The exam scores are normally distributed with a mean of 72 and a standard deviation of 9. What was Geddy's score rounded to the nearest integer? All right, so the 90th percentile means we need to find the value for P90. Okay. Go to the cumulative normal, closest one to 0.9. So here are the two numbers that it's between, 8997 and 9015. Clearly 8997 is the closest. It's in the 1.2 row and the 0.08 column. So our z-score would be 1.28. So once we know that, we can go to our formula. So x equals the mean of 72 plus our z-score we just calculated, which is 1.28, times the standard deviation of 9. And then we'll round that off to an integer. My answer key says that it's 84, but we'll verify that. Plus 1.28 times 9. Looks like that's about right, doesn't it? Nope. Does it print some crazy sizes on these things? They're at 83.52, which we then round up to 80.84. So that would be the score that puts Getty in the 90th percentile, 84. Let's move down to the next example. The annual per capita consumption of ice cream in pounds in the U.S. can be approximated by normal distribution with mean 15.4 and standard deviation of 2.5. What is the smallest annual per capita consumption of ice cream that can be in the top 25% of all consumptions? All right. And in part B says, what is the largest annual per capita consumption of ice cream that can be in the bottom 15% of consumptions? Okay, the wording can be a little tricky on this, often confuses people. Let's look at part A here. This is similar to that one where we had that cutoff score a minute ago, 2 examples ago. This is the cutoff number that puts you in the bottom of the top 25%. I mean, what's the smallest amount? So basically, the smallest amount of the top 25%, as you see in my pick graph that I've drawn, would be the same thing as the 75th percentile. So in other words, that 75th percentile puts you at the bottom of the top 25%. Then anything higher all fits in that same 25%, top 25%. So that's why that graph's drawn this way. So from the table, you see I've got the 2 values highlighted there, 7486, 7517. So the 7486 is closer. So that means P of 75 equals 0.67, which I can then calculate, put into my formula. X equals, go back up here and see what the mean and standard deviation. Mean is 15.4 plus the z that we just found is 0.67 times standard deviation of 2.5. $15.4 plus 0.67 times 2.5. Or we can do 15.4 plus, if you didn't do the table lookup, if you're using this calculator, you don't need to, 0.75 times 2.5. And that's a little bit off, but that's not going to... That's because, we're picking the closest value on the chart. We're choosing the closest one. The calculator is doing it a lot more precisely. But that will not be an issue on a test. You would not have answers that close. All right. So I'll just go with the way I've hand wrote it, so that way I'll match the calculator. There we go. But like I say, the other way would not have hurt us. Now, part B, largest amount that can be in the bottom 15%. So now we're saying essentially the top of the bottom 15%. Like, for example, you couldn't really say the top of the top 25% because it kind of goes on forever, or you couldn't say the bottom of the bottom 15%. But you can say bottom of the top or top of the bottom. And here's my graph. So actually the top of the bottom 15%, that's just the 15th percentile, whenever it's worded like that. The top of the bottom is the 15th percentile. So once again from the chart, as you can see, I've got the two values kind of pinpointed there. 0.15 is between 1515 and 1492. It's closer to 1492. So then we're going to say P of 15%, and it's on the negative 1.0 row, 0.04 column, so it would be negative 1.04. So the value that represents the top number of the bottom 15% is mean 15.4 plus this z-score of negative 1.04 times 2.5. I won't do the inverse norm for this one. I'll just do, actually, let's bring this up right there and change this to negative 1.04. Times 2.5, enter. So it looks like we got 12.8. So 12.8 pounds of ice cream for the year puts you at the top of the bottom 15%. In other words, the 15th percentile. All right, let's look at the next example. Bags of baby carrots. The weights of bags of baby carrots are normally distributed with a mean of 32 ounces and a standard deviation of 0.36 ounces. Bags in the upper 4.5% are too heavy and must be repackaged. What is the most a bag of baby carrots can weigh and not need to be repackaged? So I'm sure the business probably uses the cheapest packaging they can get away with and just hope it doesn't burst. So that's why we don't want to overload it. Plus, I guess as a business, they don't want to give them too much extra product for free either. So let me just kind of paste this little curve instead of I don't have to draw one. Just to kind of show you here. All right, so just kind of get a picture. So the top 4.5% are deemed too heavy. So anywhere in here at that cutoff point. So similar to so we're looking for the bottom of the top 4.5% again. So essentially then we want to know what's the percent to the left. Well, 100% basically minus 4.5% equals 95.5%. So as a percentage, it's 95.5. As an area, it's 0.955. So I'm going to go to the chart. I want to find the closest to 955. And, oh, well, they're going to be on two different rows, so I can't put them side by side, but 94545 and 9554. 9554 is actually a little bit closer than 9545, so we're going to go with that one. It's in the 1.7 row, the 0.0 column, so we're going to go with a z of 1.70, which I'll write this. So basically we've done this. P of essentially 95.5, what it boils down to, is 1.70, or just 1.7. All right, that's all we need because we'll have our main standard deviation every time. So we'll calculate this in terms of x, and let's see what happens. X equals 32 plus 1.7 times 0.36. +32 1.7 times 0.36. Looks like 32.612, which is the answer I have written over there. So that looks good. Now, I don't know. It doesn't specify, a certain number of decimal places. So, but I would just use that. So in other words, if it weighs that amount or higher, we'd want to break the package open and repackage the carrots. Anything less than that, we're good to go. Now, the last example, this is not a question I usually ask on an exam, but I kind of like to do this, show this, because it has to do with percentiles. And, most students are, when you talk about curving an exam, they kind of misunderstand what that means as far as, that's, well, I added 5 points to everybody's score, the exam was curved. That's really more of an adjustment. Actually, true curving of scores, and I've heard that being used where possibly in situations where exam scores are really hard, you might see something like in engineering schools where exam scores aren't all that high, and class average might be in the 40s or something like that. And then they can sort of set what percentages they want to be A's, what percentages you want B's. Now, this is assuming that the scores plot out to be sort of normally distributed. If not, this doesn't really work that well. So if you look at this example, it says, okay, and it works better with a large set of data, it would have a better chance of being normally distributed also in a big class. Smaller, it's less likely. So this says, they mentioned this example, large statistics class. The exams are distributed with a mean of 72 and a standard deviation of 9. And grades are assigned according to the following rule. So we're not like adding points or doing this. It's literally, truly a curve because it's being put on the normal curve. The top 10% of the scores are going to receive an A. The next 20% are B's, the middle 40% are C's, and the next 20% are D's, and the bottom 10% are F's. So, for example, to calculate an A, score needed for an A, essentially the top 10% means the cutoff would be the 90th percentile, the 90 that are below that. So it would be 72 plus P90 times standard deviation of 9. Now I'm just going to set these up for you, and if you want to calculate these out of curiosity, that's fine. Like I said, I wouldn't really have a question directly like this on a test, but I just want to show you this. Score needed for a B. Now if you look at the graph, you see that 20% section, but obviously the 20% plus the 10% above it, so actually it's 30% above, the 20 that represent the B's and the 10% that represent the A's. But as far as our calculation, they're 70% below that cutoff for the B. So the way you'd make this calculation is 72 plus P70 times 9. And that would tell you your grade necessary for a B. I've done this before. I might do the first one for A's just to show you. I believe it was 80-something, I believe, was a score for an A. But I'll go ahead and set the rest of these up. For a C, so you see the middle 40% are C's, and if you look at that bottom cutoff for a C, all you got to look and see is how much is below that bottom number for the C. And of course, whatever the bottom number is up to the number for the B, that means anything in that range. So that's exactly, what we're calculating is the bottom number for any range, and then the end of that range will be when you get to the next letter grade. So the 30th percentile gives us the bottom number for the C's. 30 times 0.9. Then for D, there's only 10% below a D. So whatever this minimum number is for a D, obviously F would be anything below a D, so there's nothing to calculate for an F. But let's see. I can put these in the calculator and do this real quick. 72 plus inverse norm, 0.9 times 9. 83.5. .53 would actually have been the score for an A. All right, the next one would be, let's do second enter, 0.7 times 9, so 76.71. So the range of B's would be anywhere from that 76.7 up to that 83.5. Let's do the C's. 67.28. So anything between 67.28 and a 76.72 is considered a C. And then 0.1. Anything from 60.47 up to 67.28 would be a D. And of course anything below a D is automatically an F. Well, all right, that concludes our discussion for percentiles. I wish you much success as you practice this on your own. Thank you very much.